finding volume of a solid by using the shell method. Okay, so take a look over here. This is a very thin shell over here. So imagine that it's kind of like a very thin paper roll. Okay, so we try to find the volume for this thin shell over here. We can cut along this edge and use a pair of scissors to cut along this and open that and flatten this. So we can get an object which is kind of like a rectangular box. Okay. Now, the value for this rectangular box will be length times height times the thickness. So the length over here corresponds to the circumference of the circle. Label this point on the curve x comma y. X over here is actually the average of this outer radius of the shell and the inner radius of the shell. Okay. So the circumference of that circle is going to be 2 pi x. The height over here, it is y, which is f of x. The thickness of the shell, it is delta x. So the value for the shell is circumference times height times the thickness. Now we have this curve, a continuous curve from A to B. When we rotate this curve about this y-axis, we're going to get a solid like this. Now to find the value for this solid, we can slide this up. But this time we're going to size it up so that each side is going to be a shell. So think about that as like paper roll, one outside another, okay? So now here is, you have more layer. This is one here, you have more layer, okay? And when you add up the value for each shell, you're going to get the total value here. So using Riemann sum, we're able to prove that the value for this object is going to be the integral of this 2 pi x f of x, where x go from A to B. Now, you can try to remember this. So you first label this point on the curve x comma y, and then the 2 pi x correspond to the circumference of this circle right here. F of x is the height of this shell. Dx here is the thickness of the shell. And x over here go from A to B. So the innermost shell here will have x to be A. The outermost shell over here will have this x to be B. Okay. And when you add up all those shells, you get this total value over here. Okay. So I used to have students do a 3D model of this. Okay. So you can try to imagine them. It's like one shell and another shell, you stack them together. You can use paper to make the model, okay? Now, example 1. Try to find the value of the solid obtained by rotating about the y-axis, the region bounded by y equal to 2x squared minus x cubed and y equal to 0. So y equal to 2x squared minus x cubed is this curve right here. And y equal to 0 is this x-axis. So that's the region bounded by the two curve, the yellow highlighted region. And you rotate this about this y-axis. Then you get a solid like this, kind of like a doggy bowl, okay, like this. Okay. Now, we're not going to use the dishwasher method to find the value here, because if I use the dishwasher method, I slice it horizontally. I need to find the outer x here and the inner x, and which is hard to solve for x for this equation. Okay, so we're not going to use the dishwasher method. Now instead, we're going to use the shell method. So we first get a point on the curve x comma y, and then we draw a nice segment which is parallel to the axis that we rotate about. And then let's make this thin rectangle, and then when you rotate this thin rectangle here, we get a thin shell over here. Now, in order to set up the integral, we need to find out this x-intercept here and here. To do that, we will factor this into x squared times 2 minus x. Y equal to 0 when x equal to 0 or 2. So the two x-intercepts are 0 and 2. So think about what's the value for this shell. So this is x comma y. So it's circumference times height times thickness. The circumference over here is 2 pi x. The height over here, it is the y coordinate here, okay, which is the same as f of x. The thickness over here, it is delta x. Okay. Now the value for this solid will be the integral. When you add up those shell, you get this integral. Okay. So you're integrating this. Okay. Dx over here, x go from 0 to 2. So x start from here and end it at 2. Okay. So you add up those shell. Okay. Now, because this is an integral with respect to x, you want to express this in terms of x. So y is equal to 2x squared minus x cubed. So now everything here is in terms of x. Now to find this integral, you can take out this 2 pi and then multiply this x in. Now we find antiderivative. Antiderivative this is this. Antiderivative this is x to the 5th over 5. Substituting x equal 2 and x equal 0, we got this 16 pi over 5. So that's the value for this solid over here. Okay. Example 2. Find the value of the solid obtained by rotating about the y-axis, the region between y equal to x and y equal to x squared. Y equal to x, this is this line right here. Y equal to x squared is this parabola right here. The region bounded by them will be this yellow highlighted region. We're going to rotate this region about this y-axis. So we're going to get a solid, okay, kind of like a flower, okay. So we're going to use the shell method. So draw a nice segment that is parallel to this y-axis and make it a thin rectangle. And you rotate about this y-axis, you get this thin shell over here. Let's label this point over here x comma y t for the y coordinate on top. Let's label this point here x comma y b, y coordinate at the bottom. Okay. Now, so this is a typical shell right here. Okay. The thickness of the shell over here, it is delta x. Okay. So let's use the shell method, and later we're going to use the washer method, and let's see if we get the same result. So if I use the shell method, so each shell over here will be, circumference of the shell will be 2 pi x. So that will be 2 pi x. And the height for this shell over here will be the y coordinate on top. Subtract this y coordinate down here. The thickness of the shell is going to be dx, delta x. And then the integral corresponding to the solid will be this integral. X over here go from 0 and end it at 1. So over here, end it at 1 because they intersect at this 1 comma 1. Okay. Now, so this is the shell method, right? Now let's evaluate this integral. Now because this is an integral with respect to x, let's express this in terms of x. So the y coordinate on top, y is equal to x, so that's equal to x. What about this y at the bottom? Y is equal to x squared, so that's y coordinate at the bottom here. So this subtract that will be x minus x squared over here, so that's the height. Now we can evaluate this integral by taking this 2 pi out. and then find anti-duality of this. Now we substitute x to be 1 and x to be 0 in, and do the calculation. We get pi over 6. Now let's compare this with the washer method over here. For the washer method, we're going to slice it horizontally. So each side here will be a washer. So the value for this washer over here, it is going to be pi times the outer radius square minus inner radius square. And the thickness of this washer here is dy. Okay, so remember the thickness of that is dy. Okay, and y go from 0 to 1. So y start from here and end it over here, 0 to 1. Okay. Now this is an integral with respect to y. So let's express all this in terms of y. So the outer radius corresponds to the x coordinate of this point on this curve. So this point is on the curve y equal to x squared. So solving for x, so x is the positive square root of y. Now this point over here is on this straight line y equal to x. So x coordinate will be equal to y. So this inner radius for this washer will be equal to xl, which is equal to y. Now we're going to substitute this in. So we got this integral right here. Simplify this integral. This will be y, and this will be y squared. And we find anti-duality. Anti-duality y is y squared over 2. Anti-duality y squared is y cubed over 3. Substituting y to be 1 and 0 over here. The result turned out to be, again, pi over 6. So we get the same result. But looks like in this problem, the shell method probably is a little bit easier than the washer method over here.